So because if they miss it, they can only watch the recorded of the lectures. Okay.
All right.
So I'm going to share it. Okay. About the compression behavior of soil, there is plenty of materials. It can be for master degree. It can be for B thesis. It can be, you can do this for half a year, 1 year, or 1.5 years. I'm going to explain to you, if you do it for 1 year, for B thesis, what you need to do, okay? This material is basically based on the work by me and Suki-san. And I will talk about the 5 points: the general knowledge about the compression behavior of soil. Then I will give you some literature review on the work or necessary information about compression behavior of soil. With this generally, brief talk or information, you can go to your own further detailed research and literature review, okay? And then I will suggest some plans for your thesis. You can have a choice. In the compression behavior of soil, it's not only one topic. It can be 10 or 20 different topics. So you're going to work on the general field of compression behavior of soil and choose one particular or specific area for your research or for your thesis study. I use the research because this topic is mainly theoretical investigation. So it's not experimental work. So we use the research work. Now, about the compression behavior, if you are going to study compression behavior, you need to know what is compression behavior. The compression behavior is made of, you first to know what is compression. The compression of soil, it means the volumetric deformation of soil. This is called compression of soil. But compression behavior of soil, I change that. The compression behavior of soil is the soil behavior in compression test. So compression behavior and compression test, they are different. So what is compression test? Compression test is a test that the stress ratio is kept constant in a test. So if that's the case, it is compression test. Soil behavior or compression behavior is soil behavior in compression test. So now it's very clearly, compression behavior is soil behavior in compression test. And this is the definition of compression test. So if you study the compression behavior of soil for your thesis, you need to know. So you need to be very clear what is compression test, what is compression behavior. Okay. So why I give you this topic, or why this topic would be good, is useful. It's very important is that, in study the soil behavior of compression test, we obtain the essential information. That information is needed for settlement calculation of our structures, or even the deformation of our geotechnical structures. Okay, so it means if you want to do any deformation computation, you need to know the material parameters, and usually the material parameters are obtained from compression test. So it's very important. Secondly, it is actually very complicated. It's not so simple. and there are many unsolved problems and questions on this topic. If you want, you can easily develop a PhD study on the compression behavior of soil. Now, this is a very important sentence I want to tell you, is that soil can be as soft as water and it can be as strong as steel. This will be dependent on the force ratio of the soil. And the force ratio of the soil can only be determined accurately or reliably if you can model, if you can understand the compression behavior of soil well. So you can see here, it's very important. If you can model the compression behavior of soil accurately, you will be able to determine the soil strength reliably. Otherwise, there's no point. There's no possibility you can determine the soil strength reliably. So here you can see how important the compression behavior of soil is. I emphasize this importance because you need to write it, you need to understand it. And your understanding of the importance of compression behavior will be form an important part in your thesis, justification of the your thesis and your study. Now, how is the compression behavior of soil related to geotechnical engineering problems? In the geotechnical engineering design or safety check, you need to work out the deformation of the soil. And the deformation of the soil is usually dependent on 3 or 4, if it's elastic deformation, it is dependent on 3 basic parameters. And 2 of them, lambda and kappa, are determined directly, straightforward from the compression behavior. Okay. And also, you can estimate the settlement of geotechnical structures by the compression model or compression theory. Now, in the compression model, or as we said before, compression deformation is the volumetric deformation of soil. The volumetric deformation of soil is defined by this formula. You can see it is directly linked with delta E. Delta E is the force ratio of the soil. Force ratio is obtained from this specific volume of soil. If you assume the soil skeleton is 1, then the force inside the soil particles is E. So the volumetric deformation is directly linked with the force ratio change. So now, if you want to study the volumetric deformation, you only need to study the force ratio change. This is why in our study, so in your thesis, from now, you will only concern or you only focus on the force ratio change. Because if you know the force ratio change, you know volumetric deformation. Or if you know the volumetric deformation, you know the force ratio change. You can find some basic information about compression behavior in the textbook. Okay, I'll give you some references. You can start from there to go to the detail about the compression model. Now, secondly, when you study compression behavior, how do you study it? You can study it in the laboratory. You are not going to do any test, but I hope you get familiar with the test. So please study the laboratory compression test, understand the test procedures and difficulties, problems associated with the compression test. You study this part and put this part in your report thesis, in your final thesis. And it's useful, if you, in the future, if you apply for a job, if you're doing well in one part, you can introduce your work proudly to the interview panel. Because in one part, your work will be concentrated on the theoretical analysis and the computation. You are not doing any test. But if you tell the interview panel that, even though I do all my work on theoretical investigation, I know the test very well. You tell them how to do the test. I think that will give you the edge, give you the advantage. Now, there was a special kind of test for comparison test. It's called odometer test. It is one-dimensional comparison. When you're doing odometer test, the data used is the force ratio and the physical effective stresses. Okay? So usually you use the force ratio and mean effective stress for your description. But if it is one-dimensional comparison, you use force ratio and physical effective stress. You are not going to do any test, so it's important you need to understand the test. So people see, you are fairly general, fairly comprehensive and capable. And because you are not going to do the test, you're going to obtain the test. You're going to use other people's test data. Then the first thing you need to do is obtain other people's test. You can do that by software called digitalizer. Okay, now you are going to do your thesis in the geotechnical engineering aspect. So you need to know that the stress and strain parameters used in the geotechnical engineering practice. We use the stress parameter as the mean effective stress and shear stress. The mean effective, this situation we used in your thesis and used in most geotechnical engineering computation or used in most PhD study is what we call the triaxial compression situation, where sigma-2 and sigma-3 are always the same. You can go to the details about the stress parameter and the strain parameter in the lecture notes are sent to you. So the stress parameter for geotechnical problem is mean effective stress. It is equal to the average of the three principal stresses. Shear stress, it is the difference between the major and the minor stresses. In the same way, you have volumetric strain, this is volumetric strain. You have distortional strain, it is linked with the principal strains in three directions. So in your thesis, or when you deal with geotechnical problems, please use the geotechnical stress and strain parameters. This is what we call the professional. Okay, in the same way, in the geotechnical engineering, our deformation is volumetric strain and distortional strain. The volumetric strain is linked with distortional strain by the bulk modulus. The shear strain is linked with shear stress by shear modulus. Okay, K is bulk modulus. It is linked with the unloading, reloading parameter, kappa. You will learn kappa and you will know how to determine kappa from compression model. Now, bulk modulus K, shear modulus G are linked with Young's modulus and Poisson's ratio by this formula. When you see this formula, you can see that we have 5 parameters, kappa, G, E, mu. If you can work out, if the 5 parameters are linked by 3 equations. So it says, if you know any 2 of the 5 parameters, you can determine the other 3. Or if you know any 3 of them, you can determine all the 5 of them, okay? So 5 parameters, 3 of them are essential. If you know any 3 of the five parameters, you will be able to determine all of them. But Young's modulus E, Poisson's ratio, mu are the structure engineering parameters. Kappa and G are geotechnical procession parameters. Now, for the literature review, you need to review it according to the significant progresses in the modern compression behavior of soil. So you're going to choose what model or how to review it. You choose the significant progresses or developments. In this lecture, we were concerned about the foraging compression behavior only. But the soil actually have foraging compression behavior and unloading and reloading behavior. You can go to the detail in the textbook or in lecture notes I send it to you. Now, a major part of this thesis is about the compression model. So before we go to compression model, we need to know what is a mathematical model. A mathematical model is a simplified reality. Means the actual problem is very complicated. We can't solve it, the actual problem. We simplify the actual problem, only the features of first importance we will take into consideration. Like for example, if I want to build a model to calculate your income, I maybe only concentrate on your major incomes. What is your salary? What is your constant fixed income? If it is tips or occasionally the money you found in the road, we don't put that into consideration because that's not a feature of first importance. So the mathematical model is simplified and idealized and approximated. Okay, it only considers the major feature. So, for example, if we wanted to calculate the distance, our simple model would be time times speed, but actually the speed changes. We'll ignore the difference of speed. The difference of speed variation, we'll take it as a constant. So now you are going to, the same way, you are going to model or you're going to work out the soil compression behavior. That means the force ratio of soil during compression test. So if you want to work out the force ratio of soil during compression test, you need to choose a model, okay? We will introduce you more than 5 models. You're going to choose a model for your simulation. But for this semester, for the semester 1, all of you need to choose the Skepner's model for your simulation. So for the first semester, choosing the Skepner model and be able to use Skepner model to do your simulation. Because Skepner model is the simplest one. It is the basic one. It is the most popular, the widest used model in our geotechnical engineering practice, in our geotechnical engineering theoretical research. In the second semester, you are asked, you needed to choose a different model other than Skepner model. There are many models in the world about soil compression behavior. You can choose any model. You feel it is exciting, you like to do it. When you choose a model, you need to understand the model, and then you need to work out the model parameters. And then you are going to do the model simulation or model prediction. Model simulation, model prediction, it means, if the loading on the soil changes, you can work out, you can predict what is the force ratio of the soil with loading changes. This is what we call the simulation or prediction. So you need to understand this. Is this useful for your proposal? Yes. So now you know what you're going to do. You are going to choose a model, and then you are going to work out model parameter, and then you are going to use the model for prediction. This is your plan. Only your plan is so relevant is a qualified or a past plan. Okay. So I want in your proposal, because it's week 4, week 5, you have spent so many weeks on the topic, you need to understand the topic reasonably well. Go to the details. Okay. Now, the first model is called the skepticism model. Because, as I have just said, in comparison test, we only care about the force ratio of the soil change with the stress. So usually the compression model is presented in this way. The mean effective stress, the force ratio, when soil is loaded from A to B, how the force ratio changes. If you plot the data in the normal way, you see 1.9 to 2.5, from 0 to 800, it is normal scale. It is curved. It is very curved. When we model the curvature behavior, it is a mathematical challenge. It's not easy to model it. So skepticism presents data in the force ratio. You see, 10, 100, 1000 is the logarithm of the stress scale. So in the E log P dash scale, AB is approximately linear. So what is the skepticism model? Skepticism model is that describes the compression behavior of soil in the E log P scale and assume soil behavior as linear. Okay? So this is the skepticism model. ABDF is virgin yielding behavior. What is virgin yielding? You need to go to your detailed studies. So for the virgin yielding behavior, soil behavior linearly. If it's a linear, it's a line, you can describe this line by equation. So force ratio E at any point is equal EIC minus lambda log P dash. P dash is the force ratio at any point. So you can see here from this equation, if you know the stress, if you know the force on the soil, you will be able to work out the force ratio. On condition that you need to work out the model parameter EIC and lambda. So EIC and lambda are material parameter, they are constant. For one given soil, it is the same. It's same like a Young's modulus for steel is the same. Young's modulus for aluminum is the same. So what you need to do is that if you can determine the model parameter EIC and lambda, you can predict the force ratio. Okay? So you know if you know the soil's force ratio, you will be able to determine the strength of the soil. You will be able to determine the deformation of the soil. You will be able to determine the stiffness of the soil. That's why force ratio E is so important. This is a model. A model is show you conceptually, mathematically, how to determine an unknown parameter. Here is force ratio. Okay? So this is ABD is the soil behavior during the virgin loading. BCDE is soil behavior during unloading and reloading. So unloading and reloading has a stiffness kappa. It is assumed to be elastic behavior. Okay, this is the soil behavior during isotropic compression line. So you need to know what is isotropic compression line. When you study this one, you go to this detail. That means you have some understanding of this topic. Now, we mentioned about the one-dimensional compression test. One-dimensional compression test is also called odometer test. In the odometer test, we use the vertical effective stress, sigma dash V, and the force ratio. In this one-dimensional compression test is described by this line. E is equal ENC plus lambda log p dash. You can see here, the lambda parameter is the same, whether it is in the isotropic compression line, or it is in odometer test, or it is in other proportional loading. Okay? You use this equation to describe one-dimensional compression test or odometer test. This is the first model, is scalpel model. The second model, I'm introduce some basic model. This will form a part of your knowledge and a part of your literature review. The second model is not a model, it's actually a parameter, but it has the same function as model. Boland proposed this parameter called the force ratio index. It is described as this by this equation. The force ratio of the soil minus the force ratio of soil at 100 kilopascal. You know, force ratio of soil at the stress of vertical effective stress or mean effective stress of 100 kilopascal minus the force ratio at 1000 kilopascal. Okay, this is the force ratio index. You can see here, E is a variable. It is dependent on the stress. E star 100 or E star 1000 is constant. It does not change. Star means reconstituted soil. Now you need to know that Skeptic's model is only good for reconstituted soil. So if you want to use Skeptic's model, you have to make sure your data, your experiment data is reconstituted soil data. Just like, for example, you cannot drive your car into the water. Your car is only good for road travel. Your boat is only good for water travel. It's the same way. Skeptic's model is only good for reconstituted soil. So here you need to know what is reconstituted soil. If you find that data is not reconstituted soil, don't use the Skeptic's model. Just like you don't drive your car into water. Now, based on the Boland's parameter, we can simplify the Skeptic model by this equation. Okay? So you can see, if you plot soil behavior in the vertical effective stress or mean effective stress and force index, all the soil, it doesn't matter what soil it is, all the soil will come into one line. That's the beauty, or that's the capacity of Boland parameter index. Okay. Now, if you want to determine the force ratio index, you need to know E100 and E1000. You might not be able to find the value at E1000. So what do? You're going to do by interpretation or exploitation to work out the E100 or E1000. Okay? You need these two parameters, but in the test data, you may not have the value of the two parameters exactly, but you should be able to, interpretation to work it out. Now, our further development in compression model, Skeptic proposed a linear model, then other people make further development based on Skeptic's work. They assume two segments. So instead of one line, you use A, B, B, C, two lines to represent the soil compression behavior. Some people use 3 lines, some people use 5 lines. Okay? Why does they introduce different lines? It means, soil behavior in reality is not linear. If you use one line, it may not be accurate. So in order to improve the accuracy, they use 2 lines, 3 lines, or more lines. That's the purpose. So if you can work out the line mathematically, then for any given mean effective stress, you can work out the force ratio. For example, if this is the soil's mean effective stress, you go up, it meets the line at this point, you can work out the corresponding force ratio. This is what we call the model simulation. Why you need a model? What is model simulation? What is model prediction? It means that if you have a model, you can predict it, you can work out the force ratio of the soil at any given mean effective stress. Now, for each models or each development, I have given you the references. So if you want to go to detail, you can go to the relevant reference to do more studies. Okay, now another development is proposed by Butterfield. We call it Butterfield's compression model. In the Boland's model, they use a logarithm scale for the mean effective stress called log p dash. Then in the Butterfield's field, they use log specific volume. The specific volume is 1 plus E. So the development from Skepta model to Boland model is that instead of use log p dash, you also use log V or log 1 plus E. So this is the development. Now you know the development, you know the reason for the development. That is a good point to write in your model introduction. You can tell us the logical link, the reason, the why, and the how behind the model development. That is what we call good literature review. So in the Butterfield model, you have log 1 plus E equal omega plus psi log p dash. In the same way, if you know the stress, if you work out the model parameter omega and psi, you can work out log 1 plus E. If you know the value of log 1 plus E, then you work out the value of force ratio E. A compression model is a model to help you to determine the force ratio of soil. Okay? And Marshall, now you are the only person attending the lecture. So anytime if you have a question, or if you want to discuss with me, if you want to give me comments, I can do that for you. Okay.
Yeah, I do have a question about this one. Why is there omega in the equation, but then there's the is it psi or on the graph?
Yeah, because when you go to the Butterfield model, it's log 1 plus E. These two parameters are different parameters. Right. Yeah, they're different parameters. The value is definitely different from EIC and lambda. Okay. They're different things. They have different value and different meaning. So we use different parameters. If they are different person, we give them different name. Different parameters, we give them different symbol.
Yeah, okay.
Good question. Now the further development is proposed by me and my friends Chuang and Hopkins. Our equation is, we propose a basic line. OA is the same as the Skepta's line, and AB. AB is different from Skepta's lines. So Skepta said, all the soil on the forging loading must be on the line. But based on our study, we find that soil on forging loading may not be on the line. So we propose a new model that to be more realistic. When the soil start point is not on the line, we will still be able to predict the compression behavior. It is very important. Like for example, if you want to use the GPS to drive your car, you find that your car not on the map, what you can do. So If you use the skepticism model, at the start, it's like you drive your car are not on the map. So what we said is that, when your starting point are not on the OID line, we tell you a simplified and workable model how to do the simulation. So we have 3 models. I'm not going to go to the details. I just tell you that we propose, this is a different model proposed by Liu, Chang, and Hopkins. We want to solve this problem, or we solve this problem successfully. So this is a simulation. This is actual soil behavior. If you use skeptical model, this is model simulation. It's not good. If you use our model, this is our model simulation. It is much more improved. Another model is proposed by Boland and many other people, like Professor Hong and others. So if you see in the skepticism model, in the Butterfield's model, we assume soil behavior linearly. Skepticism propose a non-linear modeling. So now you can see, Marshall, this is a change from linear behavior model to the non-linear behavior. So Boland chose this line, this non-linear line to describe soil behavior. This is actual soil behavior. And this is Boland's line. It is not exactly, but it's reasonably close. This is Professor Hong's proposed line. And if you go to other research papers, there are some more different nonlinear lines, okay? This is external data. You can see that the soil behavior in the E log P space, if the stress changes from 0.1 to 10,000, if the stress is wide enough, they are actually not linear. Linear is an assumption. The linear behavior, linear representation is simply an assumption. It's not accurate enough. Okay, let's have I'll come back in a few minutes, okay? Yeah, have 5 minutes of rest, I'll come back. Okay, Marshall, can we start now? Okay. So this another model is proposed by Hopboskin, Chang, Hong, and I. We propose an S-shaped model. Why we propose an S-shaped model? Because the actual compression behavior is not linear, it's not curved like proposed by Professor Boland. It is S-shaped. Okay. At the beginning, it's a definite value. At the end, is a definite value. It's S-shaped. This is the reality. Okay. So we propose this S-shaped model, and this is the true, correct one. All other models, you can say, in the theory, they are wrong. If you look at Skeptic's model, or if you look at many other people's model, they have some mathematical problems. Mathematical errors have fundamental errors. Okay. So here you can see, this is experimental data. This is S-shaped modeling. It is much better, not only much better, but because other models, they cannot predict it. Okay. It's not only more accurate, but they can do the impossibility. So this is all these models for reconstituted soil. So what you can see here, almost all this model, they're only good for reconstituted soil. So what is a reconstituted soil? Reconstituted soil is the soil you take from the outside, from the field, you smash, you dry it, you smash it into powder, and then you mix with water. So it's not the actual soil. You take the actual soil, you dry it, you make it into powder, and you mix it. But the most important model for the actual soil, the soil you're going to do your engineering work, you're going to do your engineering construction on it, is the actual soil, the real soil. This is what we call structured soil. Structured soil is real soil. So I and Carter proposed this model for the real soil behavior. It's called structured soil. So now, if you want to study, use like a Skeptic's model, even Boland's model, you need to know that they are only good for reconstituted soil. You can only use reconstituted soil data for your work. You shall not use the structured soil data. You shall not use Skeptic's model to predict the behavior of real soil or structured soil, because they are not suitable. They cannot do the work. So you need to make this difference. If you want to study the compression behavior of structured soil, you need to use the compression model for structured soil. And Liu and Carter's model is one of the structured models. So now you know there is a structured soil and there are structured soil compression models. I'm not going to the detail. You shall be able to study it by go to the two references. This is same development on the structured model based on Liu and Carter's model. Okay. This is the result. You can see. This is a Skeptic's model. It only predicts this behavior. But our actual soil can behave this way, this way, this way, or in many different ways. That can only be described by structure model, or you can even say can only described by Liu and Carter's model. Another model is called the DSC model. It's also proposed by Fang, Liu, Du, and Hopboskin. This model looks very simple, but it's very powerful. And the simulation, if you want to use this model, is very challenging. You need to be very good at mathematics. You will be able to use distributed compression, this DSC compression model. It looks simple, but when you use it, it's very complicated. But when you do a simulation, you can get a very, very good result. So, but this is the compression models for soil. So if you can review these models in your literature review. So here is this example, this is the actual soil behavior. This is a model predicted by DSC compression model. Okay, these are more generally DSC compression model by me and my colleagues. You can use this one, and this shows what is actual soil behavior, what is model simulation. You can find that now it is much better, much accurate. It can predict fairly complicated, fairly challenging behavior. But understand this model, be able to use the model simulation is a huge challenge. You need to be very good at programming. Okay. So now you need to know why you want to study the force ratio of soil. You need to review different model. Why we need to have different models? What's the difference between different models? Why you want to study compression behavior of soil? And how to use compression model to predict soil compression behavior, and how to use compression model for solving engineering problems. So this is the basic general information you need to know to study this thesis. Or get you obtain the base, achieve the best learning result, get the best result for you. And if you learn the best, if you achieve the best, you get the best marks. Now, suggest if you work for half a year, this is about the area topic you can you should cover in your half a year's plan. Now we will go to the 1 year frame first. If you study for your Bachelor of Engineering thesis, you shall review 5 or more compression models. When you review this model, the purpose is understanding the historical development. Why we need this model? What problem we solve? What's the advantages, deficiencies, and problems for the model? You need to use 2 or more models to simulate or to predict the compression behavior of soil. Okay, you need to at least use 2 models for a Bachelor of Engineering thesis. And then you need to compare the performance of the different models. You are going to use 2 models, you compare the difference or the performance of the 2 models. The third one, when you use a model, the first thing is that you need to learn the model, understand the model. Then the third one is determine the model parameter. So model parameter is very important. With model parameter, you can do the simulation or prediction. So when you obtain the parameter, study the parameter, if you can get some useful conclusions or experience equations about the quality and quantity of model parameter, or even you can suggest how to determine the model parameter. This is your achievement, your conclusion, okay? You determine the model parameter, and if you can perform a study about the model parameter, you obtain some useful qualitative, quantitative conclusions. That is very good. That will be your conclusion and your achievement. For example, some people studied, how the compression index lambda changing with the liquid limit. They find that the higher the liquid limit, the larger the lambda value. Or someone studies the lambda with water content. And some people even study with lambda with temperature. So you find that in the winter, how much is lambda? In the summer, how much is lambda? This is very important because usually people don't care of the value of lambda with temperature. But in some area, if the temperature changes a lot during one day, it will affect the performance or the settlement of our structure. And you study this topic, no one studied, and you are the expert in this area. You get some useful conclusions, you can tell people, because they don't study, they don't know it. So this is what we call your achievement. If you study structure soil, you can study delta EI, P-YI, and B, changing with soil structure. What is delta EI? What is P-YI? What is B? If you want to use this model, you're going to study the details, understand the model. It means you need to understand all the model parameters and be able to determine it. So all this you can choose to study. Then you discuss about the merits and deficiency of the models. Because you are going to use at least 2 models, you can study it. And because you have doing your intensive, deeper study, you understand this problem much better. So you maybe propose some further researches. Because in some way, the model is not good, or the information, the material about the model is not enough. You can propose further studies. And then you're going to discuss about possible engineering application. Okay. So the work for 1 year framework, the basic part, you need to use the linear compression model, scaffold model for simulation. So for the first semester, this is a minimum requirement. You should be able to digitalize the data and using the scaffold model for simulation. Okay. If you don't do that, it will be fair. So for the first half semester, it's very important. Use one model. Use the scaffold model for model simulation. If you want a simulation, you need to get the data first. You get the data by digitalizer. But don't worry, do it step by step. You're going to do your proposal, and then you're going to do digitalizer, and then you're going to do simulation. For the second semester, you are going to use 1 or more models for simulation. That's the minimum requirement. You can use model for reconstituted soil, you can use model for structured soil, or structured clays. Okay. Now, this part is very important about the application of compression model. You are not going to estimate the settlement of structures, but you need to know how to use the model to estimate the settlement of structure. You have learned that in Civil 462, that is Dr. Vinod's part about the estimated settlement of structures and settlement of geotechnical engineering structures. But this is next semester's work. So don't jump from level 1 to level 100. Do it step by step, everything achievable. Now, it's very important when you can digitalize data or when you can simulate data, please come to see me, show me your first digitalized data, show me your first simulated data. Why? Because if you digitalize data is wrong, all your digitalization data will be wrong, all your simulation is wrong. So when you be able to do the digitalized data, come to see me. We need to make sure you can digitalize data accurately and correctly. And you can choose, in your second semester, you can choose, the following details for your study. How soil behavior at different water content. If they are the same, that's very good. You said they are the same. If they are not the same, then what is the difference? Can you find out the difference and make a suggestion for engineers? So when the water content of their soil changes, how the compression behaves, soil can be modeled. How the soil compression behaves at a different temperature or at different loading rates. Or, if Wollongong soil, the Wollongong soil behaves, compression behavior, if you know Wollongong sand compression behavior, how about Wollongong clay and Wollongong sand mixed, how the behavior? You can study this. So all these are for further deeper studies for next semester. You need to be aware, these topics are only for you for choice. So for example, like in the second semester, you still want to use the scabbard model. You use scabbard model for study soil behavior at different water content or different soil mixture. So here you study how, when the soil is mixed in different way, how the compression behavior of soil is changed, how mixed soil compression behavior can be modeled or can be simulated. That will also have a great engineering value. And you study that topic, you get some very useful, powerful conclusions for the practical engineers. You can also choose these topics. All these topics are possible for you to select. So what I'm saying here, for the first semester, you are going to use scabbard model, but for the second semester, you're going to choose different areas, different topics. You can choose, study the influence factor, like water content, stream rate, or mixed soil, or stress level. You can use Scabbard's model, you can use Butterfield's model, you can use any model. Or you can choose model different soil structure. And you can use different model. All these are for choice. But don't worry about that. This is only for second semester work. Or you might say, okay, I only study Scabbard model. I'm going to concentrate, focus on the settlement calculation. That is also possible. Okay? Or you can go to say, I'm going to study the elastic deformation. All these are possible. Okay? This is the second topics. Conclusion, what are you going to do in your conclusion? Or what you have what will you say? If you know what is important in the conclusion, you have some idea what you're going to study, what you're going to work on in your study. For example, you need to get if you have qualitative or quantitative information about a compression model, that's a very good point for your conclusion. It is actually your contribution. So when you do your thesis, you will have this in mind. It's an important achievement if you can obtain and try to do it. Okay, and you can suggest your further researches. Okay, these are also the topics you can do it if you want. Any questions? Anything not clear? I think we stop the recording. Okay.
All right.